Okay, so yeah, as I was saying, we're going to see today, we're going to talk about the chemical risk in the laboratory and see the different tools that laboratory personnel has to get protected from the inhalation risk. So here you see, oops, sorry. We're going to start with seeing how to proceed to the risk assessment. We're going to see the different tools to get protected from chemical risk, and then we're going to look a bit more in details to two different solutions, the extraction and the recirculation. So if we start with the chemical risk, it is characterized by different factors that are present in the laboratory. So first you have the chemical properties that you can find in the safety data sheet that we should always refer to, as well as the handling condition, which allows us to determine estimated exposure level to which the chemist is exposed every day. So this exposure level should be compared to the WEL. So what is the WEL? It is the workplace exposure limit valued. That is a value that is given by governmental entities. So in France, for instance, we have the INRS that is giving these values. And they are determining, let's say, a certain quantity of chemical that chemists should be exposed in their working day. And we have two different type of workplace exposure limit values, the one on the long term and the one on the short term. So if we start with the long-term exposure limits, it is the limit value to which a chemist should be exposed during one working day. If we consider 8 hours of a work day, it is calculated on an average of 40 years of working, and it creates, this is how we determine a long-term danger for the chemist. And then we have the short-term exposure limit, which is an exposure for a duration of 15 minutes that can create immediate danger for the chemist. So here you have some examples of different WEL. So of course, the lower the WEL, the more dangerous is the product. For instance, for the acetone, chemists should be exposed to 500 ppm concentration of acetone, whereas if you take a chemical that, for instance, the glyceraldehyde, the threshold limit value is of 0.05 ppm, which means that chemists should never be exposed to more than 0.05 ppm of glyceraldehyde. The WEL are values that can be, of course, revised and changed over the time, depending on new knowledge, on new studies, on new international regulations. If we take, for instance, the carbon tetrachloride, in the past, the WEL was of 10 ppm, and now we have, it has been changed to 2 ppm. Due to the fact that new studies has been made. For the acetone, it's the same. In the past, in France, we had the workplace exposure limit value of 750 ppm in France, and now it has been lowered to 500 ppm due to a new decree. But acknowledging and respecting this WEL doesn't mean that the risk has disappeared. What is the reason to that? It is that, as you see on this picture, in the labs, it is very often that chemists are using many different types of chemicals, and we have the knowledge of the threshold limit values of one chemical, but the threshold limit value or workplace exposure limit values are specific to one product. But we don't have the knowledge of the mix of all these different products, which is the reason why it creates a danger inside the laboratory. So yeah, as I'm saying, on the long term, the danger inside the laboratory can often be neglected. Why? Because first of all, there can be a lack of knowledge regarding this WLS, and especially their cumulative effects. So the fact that we don't know the WEL for a mix of different products. Because also for some products, as we say, there's no immediate danger, but the risk come on the long term, and it is often forgotten. On top of that, over time, after maybe working 30 years in a laboratory, chemists become more tolerant towards some chemical odors, and they don't realize there's a risk anymore because they've been used to it. And finally, when chemists start to smell a chemical, it is sometimes way over already the WEL. So when we start smelling the chemical, it's already too late, let's say. So as we've seen, a daily exposure to chemical products can create a risk of inhalation, which can create potentially very dangerous illness. If we take, for instance, the nitric acid, it can over time destroy tissues or damages vision. So there are some studies that has been made in the past that shows that, for instance, 16% of the pregnant laboratory technicians can suffer from fetus malformation, according to the American Medical Association study. That is to really realize that there's risk in the laboratory and they need to be assessed. So first step is to understand the risk present in the laboratory, and the second is to choose the right protection tool. So now we're going to go to the different protection tools that are available for the laboratory personnel. So we have the not ventilated tools that can be composed of the ventilated benches, the canopy hood. They are not ventilated because they don't have any enclosure. And then we have the ventilated tools. So for instance, a ducted fume hood or ductless fume hood or ventilated storage cabinet. So what is their efficiency and how are you protected while using them? So for the not ventilated tools, so as I was saying, the ventilated benches, the mobile fume extractor, there's a limited protection of the laboratory personnel. The reason why is that it is because there's no enclosure, which creates no containment. And that means that there is no barrier between the operator and the product. On top of that, there's no norms that are regulating this kind of tools. Now we're going to move to the ventilated tools that are composed of, as I was saying, the ducted fume hood, ductless fume hood, the storage ventilated storage cabinet. These are approved by different criteria, performances that we're going to see a bit later. They provide protection thanks to a good containment. So why chemists or laboratory personnel should use a ventilated enclosure? Because it is the only way to create an effective barrier between the operator and the chemical vapors and to ensure their containment. Chemical gases, as well as powders, they can spread very easily and quickly in the air in a multidirectional way if there is no ventilated system and no enclosure. So the ventilated enclosure, they allow to capture gases and powders with the help of the unidirectional airflow, and they allow to contain all the chemicals into an enclosure and to blow them out by ventilation means. So now we're going to look more in details to the extraction or the recirculation. There are two different ventilated tools. So yeah, as I was saying, both these options are a ventilated enclosure. So the two different tools that we see here is the ducted fume hood that is working with the external exhaust system, and the filtration fume hood that is working with the filtration and the air recycling. The working principle of a ducted fume hood is that chemicals are handled under the enclosure, and then all the polluted air is extracted through a fan that can extract around 800 to 1,500 cubic meter per hour, and it extracts this polluted air. But as you can imagine, the air needs to be compensated back inside the laboratory to keep a good pressure, which means that the air that has been extracted will need to be introduced again inside the laboratory. So as you see here, there's a fresh air supply fan that will bring back the same amount that has been extracted inside the lab. It can be warmed or cooled down, depending on the country and on the season. To check the safety and as a proof of safety of the good containment of ducted fume hood, there's a test that is made that is called the SF6 tracer gas test, which means that the SF6 tracer gas is emitted inside the enclosure of a ducted fume hood. And according to the European standard EN 1475 and the French standard NFX 15211, the concentration of SF6 should be of 0.1 ppm maximum to make sure that there is a good containment and that the chemist will be protected while using this ducted fume hood. So now we're going to move to the filtration fume hood. So it is working with HEPA and activated carbon filters, and there's two different performance criteria that can be used to check the safety of this device. So first, for the molecular filtration efficiency, it is done through the AFNOR NFX 15211 standard that states that the concentration should always be below 1% of the workplace exposure limit value found in the exhausted air during the normal working filter lifespan. Which means that if, for instance, we take the acetone that has, as we've seen before, workplace exposure limit values of 500 ppm, we know that the concentration to ensure the safety should always be of 5 ppm, which is 1% of the WEL of the acetone, which means that we are going to consider that a filter is saturated as soon as it reaches 5 ppm of acetone. So which gives a margin of 495 ppm before there's really a danger for the chemist. And then for the particulate filtration efficiency, we have the standard EN 18221, which states that the global filtration efficiency for particles that are bigger or equal to 0.1 micron is of 99.995% while using H14 filters. So as you see, you have two different options, but what is the advantages and what is the inconveniences of both and how to choose. So we're going to first have a look at the ducted fume hood and the protection that you get thanks to it. So the main advantages of a ducted fume hood are that it allows you to handle large quantities of chemicals, as well as all types of oops, sorry, did wrong manipulation, sorry. It allows you as well to handle all type of liquid chemicals. The inconvenience is mostly regarding the energy consumption that we've seen previously. As I was showing in the graph before, there is a need for air compensation inside the laboratory when there's ducted fume hood that are used. The air that is brought back inside the laboratory creates, of course, a huge energy consumption. So there are some studies that has been made regarding this subject. For instance, there is a study that has been made on a German car manufacturer that is using ducted fume hood, and considering 220 working days, the consumption of the ducted fume hood was of around 5,500 euros per year. Of course, it depends on the age of the building, of the age of the building, sorry, of the age of the ducted fume hood. For instance, in the Italian Research Institute, the fume hoods were the ducted fume hoods were consuming more around 2,200 euro per year. But as I say, it really depends on the age of the fume hood, on the building, etc. Another inconvenience to the ducted fume hood is that there's direct emissions of toxics into the atmospheres. As you can imagine, the polluted air is extracted from the fume hood and goes outside, so in the air outside the building. So that is not, first of all, good for the planet, not good for the people that might walk around the building, but there's also a risk of toxic reintroduction into the building. As I was saying, some air needs to be introduced back into the building to make a compensation of the air. So there's a risk that this toxic are reintroduced later on through through the building. Finally, powders handlings are not really recommended under ducted fume hood. And it is fixed to the ducted system. So as you know, the ducted fume hood need to be placed exactly under the exhaust system, which makes it compulsory to plan for the installation beforehand, because the building needs to be adapted for it. So the projects needs to be decided way in advance to be able to plan for the installation of the ducted fume hood. And once it's installed, it's very hard to relocate in case that there's a modification of the laboratory work. So yeah, if a laboratory decides to either build a new room or change the configuration of different machines, it's not possible to change the place of the ducted fume hood, as we say, they need to be fixed to the ducted system. They have high installation and running cost. Here you have all the different numbers. They correspond to all the different devices that needs to be installed when you want to work under a ducted fume hood. So as you see, for instance, you need to have the ducted fume hood, of course, but you also need the external ducting system, the extraction fan, the duct, the air supply fan, the air conditioning with filtration of fresh air. So all these different devices, they lead to an average installation cost of a ducted fume hood of 15,000 euros. You also have yearly running costs that are mainly composed of the energy consumption and the energy cost, of course. So as we were saying previously, they depend on the building, on the fume hood, the age of the fume hood. But we can as we said so previously, they can be between 2,000 and 4,000 euros per year. So just as a small resume of all the different points we've seen previously, the main advantages that all types of liquids can be done under a ducted fume hood. There's large quantities that can be handled as well. So there's no need to be preoccupied by that because it gives protection for all types of liquids chemical. The inconveniences are the huge energy consumption, the fact that it's polluting the air because the toxics are just released into the air right after being extracted. It is fixed to the exhaust system. It is not possible to relocate it in an easy way. It has expensive installation and running costs due to the fact that there are many devices around the ducted fume hood that needs to be installed so that it's working properly, and as well as high running costs due to the high energy consumption. And then finally, if powders needs to be handled, it is not really recommended. So now if we go to the filtration fume hood, so the ductless fume hood that are independent fume hoods not connected to the exhaust system. The main advantage is the protection that it gives to the user, and that is granted by the class 1 fume hood. So according to the NFX 15211 standard. So the class 1 fume hoods are fume hoods that are composed of 2 layers of filters, a main filter level and a safety backup filter with a saturation detector after the main filter level. These 2 layers allow to avoid any release of toxic into the lab when the main filter is saturated, because when the first filter is saturated, you still have a backup filter that will make sure that there's no release of toxic into the lab. The second main advantage is that it is protecting the environment. We know where the toxic are going. They are trapped into the filters. They are not released into the atmosphere. It is an immediate availability of these fume hoods because there's no need to do any duct work. So if, for instance, building a new laboratory that has no exhaust system available, then the ductless fume hood can immediately be used without having to change the laboratory. And there's as well easy relocation as it is not ducted to the exhaust system. So for instance, if there is some work in the laboratory, it's easy to just place the fume hood somewhere else. There's a very low energy consumption, a bit less than 50 euros per year for the bigger of the unit. Sorry, it is just plugged into the sockets. So this is the only energy consumption. There's no installation cost and no forward planning for ductless fume hood. The average cost for the purchase of a filtration fume hood is about 4,500 euro. For the running costs, it is composed mainly of the filters that needs to be replaced, around 400 euros per year. Inside a ductless fume hood, liquids as well as powders, chemicals can be used. They can be used individually or combined. The reason why is that on a ductless fume hood, you can play with the configuration of the filters. So HEPA filter as well as activated carbon filters can be used, either individually, as I just said, so only HEPA filters or only activated carbon filters, but we can also make a combination of these filters, depending on the needs and on the handlings. The framework, the limitation of a ductless fume hoods are that not all chemicals are trapped by the filters. There are some chemicals that are not retained by activated carbon filters. Some examples are the carbon monoxide, the nitrogen monoxide, or the hydrogen. In this case, you will not be having protection from a ductless fume hood. On top of that, filters do get saturated, so there's a need for the detection of this saturation. So all manufacturers of ductless fume hood should provide the user with a method that will allow them to detect independently the saturation of the filter. So yeah, as I was saying just a bit previously, there's a replacement of the filter, replacement frequency. That means that there's a need of having new filters and of changing them. And as we've done for the ducted fume hood, we're also going to recap all the different advantages and limitations of filtration fume hoods. So the main advantages are the high energy savings that are done because it is only plugged to the socket. There's no toxic emission inside the atmosphere. There's an immediate availability of this devices. There's low investment and running costs. They are adapted for liquids and powders, and they have enhanced standard requirements since 2009, which guarantee the highest level of safety. For the limitation, as I said previously, there are different type of products handled that are not being trapped by the activated carbon filters, and there's a need for saturation detection. And here you have them again, but it is what we have talked about previously, the protection through the class 1 that brings a safety layer of activated carbon, which will always trap any toxic, even if the first layer is getting saturated. And the environmentally friendly side of the ductless fume hood, as their energy consumption is so low, as well as the fact that there is no toxic release into the environment, into the atmosphere, high energy and cost savings, as we've seen before, and the mobility that is required more and more in the laboratories. So how would you make the choice? Like, how can you decide if a ductless fume hood, a filtration fume hood, is a serious safety solution for you? Well, the answer is that it is a serious safety solution for you if all the conditions that we're going to see now are respected. So first of all, a clear description of the intended usage defined by the user. So this is crucial, and a description of what is going to be done under the fume hood, and the type of handling, the type of chemicals that is defined by the user himself, that is going to describe it to the manufacturer. Then a feasibility analysis conducted by the manufacturer's laboratory. So analyzing if it is actually possible to use a filtration fume hood. Is it adapted for the laboratory handling? So really this analysis done by the laboratory to make sure that it is a safe solution for the specific laboratory. And then a written certification issued by the manufacturer after the analysis that is going to give different information to the user. So first of all, the right filtration typology that is guaranteed by the laboratory, calculated filter lifespan that is given to the customer even before using the fume hood, and as well as a certificate that is going to guarantee the user safety according to the most stringent standards that we've seen previously. So the choice of filtration fume hood should be based on the commitment that the manufacturer shows to the user, shows that through the description, through the analysis, and through the certification that are going to prove to the user that they have commitment from the manufacturer for their safety. So just to conclude on what equipment tools should be chosen by the laboratory personnel, should we use a ducted or filtration fume hood? What is the safest? The answer is that both fume hoods need to be used inside the laboratory, ducted and ductless fume hoods. The ducted fume hoods should be used for all the uncontrolled evaporation. That is the evaporations that we don't know about. That is like when chemists are not going to be able to give a precise description of what is going to be done inside the laboratory. And ductless fume hood should be used for everything that can be controlled, so everything that can be described by the user beforehand, at the beginning of the process of buying the fume hood. In any case, to choose between a ducted or a filtration fume hood, what is important to keep in mind for both solutions is that a risk assessment should always be made for both solutions, understanding the risks that are present in the laboratory for the laboratory personnel based on the workplace exposure values. A feasibility study, checking what is the best option, understanding what is going to be done under the fume hood, and then some processes adaptation will make the optimized choice. And now I am done with the presentation. I hope you enjoyed it, and I am open for the questions now.
Why is powder handling not recommended in a ducted fume hood?
So the powders can be trapped later on in the exhaust system, which can create a risk because they are not really extracted into the atmosphere. They just get stuck inside the exhaust system. So they are not really disappeared. They are just stuck in the exhaust system.
So that's right. And this is also what Alice just mentioned, Kate. This could be a problem for when there is a maintenance. The fact that toxic powders could be stuck in the exhaust system, in the fan, or it could really be a problem, a concern for the safety of the people who are actually gonna do the maintenance. And you also have to know, Kate, that some, I know that we are really in your topic, knowing what you could do under fume hoods, but some powders are, you are not allowed to handle them under a ducted fume hood. There is an official classification. I don't know if you are aware with occupational exposure bending, and there is a hierarchy of occupational exposure limits depending on the risk, and some of the requirements depending on the powders and the toxicity. They are not allowed to be handled under a ducted fume hood. So I hope it answers your question.